everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am dealing with the course Computational Aerodynamics. In today's topic, we will see the definition terminology on the module 4, which is CFD techniques. So, in the previous sessions, we have seen the definition terminology for the module 1 and the module 2 and module 3. So, where in the module 1 we have discussed about the types of control volume and the fluid flow element approach. These aspects we have seen. In the module 2, we have seen the nature of the PDEs. In that, we have seen especially elliptic, parabolic, and hyperbolic equation. In the module 3, we have seen difference between the explicit and implicit approach, where we have derived these equations from basics of Taylor series of expansion. So using discretization, like we have converted the partial differential equation to the linear form. So this is what we have seen till now. So in today's session, we will see how the CFL number will exhibit a major role in CFD techniques. Okay. So basically, the definition terminology question for the module 4 is, so what is the role of CFL number? So basically, what is CFL number, and how this CFL number will play a major role in governing the fluid flow problem for the stability aspect. Okay. So in the previous session, we had already discussed about the discretization process. So where we have converted the partial differential equation PDE to the linearized form. So let us take an example, dou u by dou t, which is equal to alpha into dou square u by dou x square. So this is what we have. Dou u by dou t is equal to alpha into dou square u by dou x square. So for this is a parabolic problem. So where a is equal to alpha and b is equal to 0, c is equal to you have 0. So therefore we have b square minus 4ac, so which is equal to 0 square minus 4 into 0 into 0, so which is 0 actually. So with this we can say that this 1D unsteady diffusion equation is a parabolic problem. So for this, we will see what is the condition of CFL. So CFL number, current Friedrich-Lewis number, so basically is an important number which will govern the stability. So we need to give or impose the conditions on time step and on the space step, which is delta second. Okay. So here we have u of I to the power of n plus 1 minus u of I to the power of n divided by delta t, which is equal to alpha into, which is u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n divided by delta x square. So this is what we have. Okay. So for this problem, let us actually see what is the condition of CFL. Okay. And how do we get the importance of delta t and delta x, we will see. Okay. So here in this problem, what do we have? So we can actually, we have u of I to the power of n plus 1 is equal to u of I to the power of n plus alpha into delta t by delta x square into u of I plus 1 to the power of n minus 2 u of I to the power of n plus u of I minus 1 to the power of n. So this is what we have. So this is the value which is the unknown parameter. We don't know this. We know this value. We know this delta t. We know delta x. We know u of I plus 1 to the power of n. So we know u of I to the power of n. We know u of I minus 1 to the power of n. So these values are the known parameters and this value is the unknown parameter. Okay. So here the delta t and delta x are playing a major role to govern the fluid flow in a particular cell. Okay, so you can see that delta x corresponds to the distance between the grid points. Okay, so you take this is one grid point, you take this is another grid point, take this is another grid point. So here the distance between, let's say, grid point 1, 2, 3. So between grid point 1 and 2, it is delta x. Let us say is x1, 2 and 3 is delta x2. So delta x1, delta x2, basically if they are equal, so we call it as uniform mesh. So basically the meaning of uniform mesh is, so the spacing between grid points, so you take along x direction, you take along y direction, so they will be same actually. So that is the meaning of uniform mesh. Now, so what is the concept of delta x actually? So here the spacing between the 2 points, if it is large, so delta x will be high. So if the spacing between two grid points is very low, the delta x will be low. Okay, so this is what we have. So if it is large between 1 and 2, so delta x will be high. If it is small, so it will decrease. Okay, now so alpha, let us take it as a constant actually. So okay, the diffusion constant, or you can take anything. So here this parameter, so let us take it as C, okay, which is alpha delta t by delta x square. Okay, so here alpha you can take it as constant, delta t you can actually cannot take as constant. There are two kinds actually. So while running the simulation, you can choose an adjustable simulation time step. Okay, so delta t can be changed in two ways. You keep fixed when during the simulation, or you will change while simulation runs actually. So how we can do, we'll see actually, or why we will do, we'll see. So let us take one condition. So basically we have alpha delta t, let's say delta x square. So this condition, let's say you have less than 1. Okay, this condition, let's say it is less than 1. Now what happened actually? So we have this. So here what happened? Let us take line 1, 2, 3, 4, 5, 6. Let us take, these are the grid lines 1, 2, 3, 4, 5, 6. So the distance between 1 and 2, 2 and 3, 3 and 4, 5 and 6. Basically they are changing. They are not all equal. Now when this fluid particle is going from one cell to other cell, let's say in this way it is going. So what is the time taken to cross this cell? Let us take it as delta t1. So other cell is delta t2. So on, delta t1, delta t2, delta t3, so on will be there. So if the cell size is very less, so if the time step is, let's say, is more, so by the time it captures the fluid flow phenomena, it crosses the point. So that is why, so in order to make the consistency, so a condition is given such that, so the alpha, let's say you can take it as u delta t by delta x. So we have a core number called coordinate number, so u delta t by delta x, so where this number should be less than 1. So therefore what happens actually, so whatever the fluid particles you take, so it should lie within this cell actually. Okay, so this actually is helping the fluid to remain within a time step in the cell. Okay, if not, it just crosses or passes away fast. Okay, now, so what happens if you take more than, so you have like instability in the sense, so there are conditions where the error grow with respect to time. Okay, the error will grow with respect to time, and the consistency is not followed. the convergence is not satisfied. Okay, so therefore the CFL number is playing a major role in determining the stability of the numerical scheme. Okay, so you take any numerical scheme. So we have piezo, let's say, and you have pimple next. So these are basically uh, the numerical schemes which corresponding to the transient solvers, basically transient solver in the sense, so time dependent solvers. So piezo, pimple, so basically these are the transient solvers which are time dependent solvers. So for the time dependent solvers, so the CFL condition is very important. So there is one more scheme called simple semi implicit pressure linked equation. So simple semi implicit pressure linked equation. So this scheme basically is used for the steady state solvers. Okay, so if you see the numerical techniques, like let's say the procedure to solve schemes, so basically you have simple scheme, next you have piezo, next you have pimple. So out of these two are depending on delta t. Delta depending on delta in the sense their coherent number is calculated at each and every time step. Sorry, at each and every iteration, and then you need to evaluate such a way that the coherent number is always less than 1. So we need to maintain that. So if you are not maintaining that coherent number less than 1, so we will actually the simulation if we impose a condition to jump out, or let's say it to come back, so therefore it will come back. Okay, so when we perform a simulation, numerical simulation for the transient solvers, so the delta t is playing a major role. And you have simple, so where here you will give the delta t in the sense the simulation time. So let's say you have t is equal to 0 seconds and tf is equal to final is equal to, let's say, 3000 seconds. Okay, so for this time, so what is the interval? So let's say initially it is 0 seconds. What is the next step? So if you take delta t as 1 second, so it will be 1, 2, 3, 4, so on, 3000. If you take delta t as 5 seconds, let's say first time step t1 is equal to 0 second. So next time step t2 is equal to 5 seconds. So t3 is equal to 10 seconds. So t4 is equal to 15 seconds. So on it will go till, so tf is equal to 3000 seconds. So basically within, so depends on the time delta t step, your number of times, like whatever the simulation runs, so it depends actually. Okay, so whereas for the simple form, simple semi implicit pressure linked equation, so for this we will fix the delta t, and there is a study called time independent study, or let's say time convergence. So why we do time convergence, time independent study is, here let us take you have simulation set of 3. So you have S1, S2, S3. So S1 has number of grid points N1 as 1 million, and S2 has number of grid points N2 as 2 million. S3 has number of grid points N3 as 3 million. Okay, now for this actually, so we will perform first the grid independency study. Grid independency study in the sense, when you compare the results of simulation between S1 and S2, so if there is any difference, then we'll jump to S3 and S2. So let's say the difference between S1 and S2, the numerical results error is greater than 10%. So then we don't go for S1, we will avoid it. So next we will take S3. So let's say the error between N2, let's say S2 and S3, error, if it is less than 5% or 2%, let's say it has come around 1.4%, so people think a considerable amount of error has come, so people stop the simulation here itself. So they will take that. So n2 is equal to 2 million. So the number of grid points ideally to perform simulation with an optimal mode is 2 million. Okay. So the next step is the time independence. So given the number of grid points, here again you will take 3 times delta t. Delta t1, let us take, you are taking it as 0.5. So again delta t2 you will take it as, let's say, 0.25, and delta 3t you can take it as 0.125. So you are making it half every time. Delta T1, delta T2, delta T3. So this, you will compare the results between these two. Okay. So if the error has crossed, let's say, greater than 10%, so what you do is like you will avoid delta T1. So you will compare these two. So let's say the error, if it is coming less than 4%, 3% or 2%, let's say the error is 1.5%, you will, okay, let's say you have performed one more simulation which is delta t4. Okay, so for this between delta t4 and delta t3, if error is decreased, let's say 0.1 or 0.001%, so what we do is like we will take this delta t2 as the optimal time step. Okay, so why do we take this actually? What happens if we take delta t1? So if you take delta t1, let's say you will over predict or under predict the simulation results. So when you are performing the numerical simulation, so the accuracy of the simulation is very, very important, and the convergence of the simulation is very, very important, and the consistency of the simulation is very, very important. So if the consistency and the stability is maintained, automatically the convergence of numerical simulation will happen. So therefore, this is why we will actually see the majority of the time independent study for the numerical simulation. Once we fix an optimal delta t, so we will run the numerical simulation. So with this, we have seen what is the basic importance of CFL number. So for the numerical schemes, so the physical significance is CFL number is playing a major role in stabilizing the numerical schemes, which actually in turn it will depend on the convergence criteria. Then, so the CFL also will impact on the uh, accuracy of the schemes. So the CFL number condition imposing for the transient solvers is very, very important. Okay, so in the next module, so we will see the importance of the finite volume technique. So we will discuss some definite terminology questions on the module 5. So with that, we will finish the module 5 question definite terminology. So therefore, we will wind up the definite terminology for the course computational aerodynamics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.